So next we're going to look at solar PV or solar photovoltaics. Photovoltaics are classes of materials or devices that are capable of converting the energy contained in photons of light into electrical voltage and current. So most solar cells are made up from a semiconductor material such as silicon or germanium that have been doped to obtain N-type and P-type materials. So in an N-type material, a small amount of phosphorus is added to the semiconductor, such as silicon, via a process called diffusion or implantation. So we've got a normal piece of silicon. We then somehow inject phosphorus into it. Purpose of how that's done not too important. You just have to accept that phosphorus now exists inside the silicon. This process is going to result in a material. After the phosphorus kind of bonds with the silicon, we're going to result in a material that has freely available electrons. So we're showing we've got some sort of N-type semiconductor. It's silicon. It's had phosphorus injected into it. What this results in is a bunch of electrons that are free to move around. They're not bound to any atoms inside the structure of the silicon anymore. And therefore, these electrons are easily moved under the influence of voltage. They're not held by the nuclei of the atoms from which they originated. These free electrons are typically called N-type charge carriers because they have a negative charge. A P-type material, in contrast, is created when boron is added to a silicon or other semiconductor, which results in a material that has fewer electrons than necessary to complete filled bonding structures. Typically, this is a covalent bond that occurs in here. We add this boron into the silicon lattice. It creates basically vacancies in the covalent bonding structure. These voids in the atomic bonding are called holes, and these holes are free to move around the crystal lattice of the P-type material in the same way that the electrons are free to move in the N-type material. It's a little different phenomenon. The motion of holes occurs because electrons can fill holes, but when they do, they must leave a vacancy in the crystal structure, creating a new hole, and therefore net motion of the hole. When I first learned about this, the example of students in a classroom with an empty desk was used for me. Say there is one desk that is empty, and a student chooses to move to that new desk. Well, that vacated the desk that the student was in, and now another student can be free to move to that location. Now imagine the same situation, but with multiple empty desks. We can therefore kind of envision that instead of the students moving around, it's the vacancy of a student in a desk that's moving around. And that's what we mean by the concept of holes. It's this vacancy in the crystal structure that's moving around, creating a hole, and because they can move, we have a net hole motion underneath or inside of the P-type material. In a P-type material, each hole is considered to have a net positive charge, which is equal in magnitude to the charge of an electron, but it has the opposite sign. When a P-type material and N-type material are placed in contact with one another, or more typically when they are fabricated on one on top of another, such as in a solar cell or a diode, what is created is called a p-n junction. It's an interface of a P-type semiconductor material and an N-type semiconductor material. Immediately upon creation of a p-n junction, a charge imbalance exists across the junction. We've got a high concentration of holes in the P region, and we've got a high concentration of electrons in the N region. What's going to happen then is holes are going to diffuse from the P-type material into the N-type material, and electrons are going to diffuse from the N-type material into the P-type material. Since these charge carriers are mobile, since they're moving, they create a current, and this, we got holes going this way, we've got electrons going this way. This is called a diffusion current. As they diffuse, as the diffusion current flow across the junction, electrons and holes are going to recombine with the opposite carriers on the other side and thus disappear. These electrons, in essence, are going to fill the vacancies that the holes have, and these holes are going to fill the vacancies that the electrons have, and then they're going to recombine, and this is called recombination. So what happens is, at this junction, at the p-n junction, electrons are flowing under a diffusion current in this direction, recombining over here with the holes. These holes are flowing in this direction, recombining with the electrons, in essence annihilating themselves. And this process is known as recombination. It takes place near the p-n junction and results in a region of silicon material that is depleted of both free electrons and free holes. We call this the depletion region. We notice that the depletion region in the n-type material has a net positive charge because its compensating electrons have been annihilated. In contrast, the depletion region in the p-type material has a net negative charge because its compensators have been annihilated here. These are fixed atoms. These circles here, the black circles, the white circles and the black circles, these represent mobile charge carriers. After recombination occurs, we have fixed atoms in the n-type material. We get a region of net positive charge on the inside of the depletion region, and we have a net region of negative charge on the p side of the depletion region. So what happens then is inside that depletion region, a net charge exists due to the uncompensated fixed charges, the minus signs and the plus signs here, associated with the silicon structure. Thus, an electric field gets established here. It's established in the depletion region, and what that electric field does is, remember, electric fields point from positive to negative. It is going to prevent any further diffusion of charge carriers across the depletion region, resulting in an equilibrium condition. So this actually happens pretty much instantaneously. I create a p-n junction. What happens is I've got a bunch of mobile electrons over here. I've got a bunch of mobile holes over here. I've got an electric field due to the uncompensated region, we call it the depletion region, that prevents any further diffusion currents from flowing. So this is the steady state condition. If you were to somehow look at a p-n junction that was fabricated with a microscope and could see all the charge carriers, this is the condition that exists after fabrication. Electrons and holes can't move across this barrier unless they're imparted with a sufficient amount of energy to move across it. And the energy that's necessary for either electrons to flow this direction or holes to flow this direction is called the band gap energy. It's the minimum amount of energy necessary to move a charge carrier across the barrier region. We have to overcome this depletion region electric field, so we have to introduce a certain amount of energy. It's called the band gap energy of the semiconductor device, right? When a voltage is applied to a p-n junction, current's going to flow from the p side to the n side, but not in the reverse direction. This device you're probably familiar with. It's called a diode. And the voltage characteristic curve for the diode is described by what's called the Shockley equation. So the Shockley equation, if you haven't learned it already, it's the diode current ID is equal to I0 times E to the QVD over KT minus 1. Very, very famous diode equation. In this equation, ID is the diode current that flows from P to N. VD is the voltage applied from the P side to the N side. I0 is called the reverse saturation current. Q is the electron charge. It's equal to 1.602 times 10 to the minus 19th coulombs. K here is Boltzmann's constant. It's 1.381 times 10 to the minus 23rd joules per Kelvin. T is the junction temperature in Kelvin. So the only thing I'm going to explain a little bit further is this reverse saturation current. If I were to reverse bias this p-n junction, it's the amount of current that flows through the diode if it's reverse bias. It's typically very, very small, 10 to the minus 6 amps per centimeter squared of junction area is a pretty typical value. So let's just take a minute, let's pause and do an example. We've got a p-n junction diode. It's at 25 degrees Celsius. It's got a reverse saturation current of 1 times 10 to the minus 9 amps. We want to find the voltage drop across the diode when the diode's not carrying any current, when the diode's carrying 1 amp of current, and when the diode is carrying 10 amps of current. So let's just rewrite the Shockley equation, ID. It's equal to the reverse saturation current, I0. We then multiply it by E. It's an exponential function, E to the QVD divided by KT. Right? All this is to the exponent. We subtract off 1. So now let's put in some terms. We've got ID equals 0 equals we were told 10 e to the minus 9 got E to the Q. What was Q? It's the electron charge, 1.602 times 10 to the minus 19. I need to multiply that by VD. I get K, which is Boltzmann constant, 1.381 times 10 to the minus 23rd. I need to multiply by T. In this it was given as 25, but we need to convert that to Kelvin. That's 25 plus 273. And then we subtract 1 off that whole exponential value. So we divide 0 by 10 to the minus 9. We get 0. So we find 1 is equal to E to the VD. We then find, if we were to take the natural log of this term, we would find out that VD in this case is equal to 0, right? Which should have been obvious. ID, if there's no voltage applied, there's no diode current. What about the other situations? Well, we've got VD for the 1 amp situation is 1.381 e to the minus 23. We then multiply that by the temperature converted into Kelvin, which is 25 plus 273. We now need to divide that by 1.602 times 10 to the minus 19th, the electron charge. Right. This is going to be multiplied by the natural log of 1 amp divided by the reverse saturation current, 1 e to the minus 9. And then I add 1 to that. And that's going to give me a value of 0.532 volts. And so if I apply if I apply 0.532 volts to this PN junction, I'm going to get 1 amp of current. And then for 10 amps, it's the same equation. This stuff's all the same, but it's going to be the natural log of 10 amps over 1e to the minus 9 plus 1. I solve for that. I get VD equals 0.592 volts. Right, so you get if I apply 0.592 volts, I get 10 amps. So very small increase. 0.06 volts increase gives me a factor of 10 increase in the amount of voltage flowing across this PN junction. And you know what you should know from a diode, right? If I plot I versus V characteristics, it looks like this, right? And the Shockley equation governs the shape of this guy right here in the forward bias region. There's also that reverse saturation current, I0, right? Purpose of this class isn't semiconductor physics, but maybe you learn a little bit from that. Okay, so now let's look at the action of the photovoltaic cell specifically instead of just the generalized PN junction. What happens in a photovoltaic cell is that a photon is incident onto the N side of the PN junction. When that photon strikes the surface of the N-type material, if the energy of the photon is above the band gap energy, an electron hole pair is formed in the N-type material. These electron hole pairs are mobile and are free to move under the influence of the electric field established by the depletion region. What this results in is the movement of the electrons, or accumulation of electrons in the N-type material, and an accumulation of holes on the P-type material. This charge separation of these accumulated electrons and these accumulated holes creates a measurable voltage that can be used to deliver current to a load. If an electrical connection is made to the N-type and P-type materials to form an electric circuit, electrons will flow out of the N side through the wire, through the load, and then back to the P side. Whoop. By convention, positive current flow is in the opposite direction to actual electron flow. So the current in a solar cell is said to flow from the P side to the N side, despite the fact that it's actually electron flow that's causing a causing current to flow. So just to summarize, what happens? Some sort of photon strikes the N-type material. What then happens is an electron hole pair is created in the N-type material due to the depletion zone, due to the electric field built into the depletion zone. Holes are sucked across the depletion zone into the P-type material, resulting in a collection of holes in the P side. The electron is repelled by the charge separation in the depletion zone. We get a buildup of these electrons on the other side. So then we get this charge separation. We put a circuit there, electrons then will flow. Due to the buildup of charge, they'll be attracted into these holes, creating current flow. Electron flow is from the N-type to the P-type, so conventional current flow is in the opposite direction from P-type to N-type. The most simple electrical model, or electrical circuit model for a photovoltaic cell is a diode in parallel with an ideal current source. The current source delivers a current that is in proportion to the solar flux experienced by the cell, and the circuit model is characterized by the current that flows when these these cell terminals are shorted together, and this is called the short circuit current ISC. And the voltage across the terminals when the leads are left open, which is called the VOC, the open circuit voltage. When the leads of the PV cell are shorted, no current will flow in the diode because that voltage will be 0 volts, so no voltage drop across the diode. All of the current flow from the ideal source, ISC, is therefore flows through the shorted leads here, since there's no voltage drop here. This short circuit test gives us the value of ISC here in our circuit model, and we can write the following KCL equation for the solar cell. I short circuit, that's this guy, I don't know why that says IL, that should be I short circuit. ISC is equal to, I is equal to ISC minus ID. So I've got some sort of short circuit current, which is the current that'll flow if I short those two terminals together. No current will flow in this branch because VD is 0. So under a short circuit condition, the current measured in this branch is ISC. It's the current deliverable by this ideal current source. Under normal operating conditions, I here is equal to ISC minus ID. We can substitute the Shockley equation into the KCL because ID is a diode current, so we get this is equal to ISC minus the Shockley equation, which was just I0, times E to the QVD over KT minus 1. In the solar cell, this short circuit current here is proportional to solar insolation, or how many watts per meter squared are shining on the solar cell. And this equation very accurately describes the operation of the photovoltaic cell under varying amounts of sunlight. So here what we have is we've got this equation plotted for a certain amount of solar insolation, and what we've done is we've plotted the amps versus the open circuit voltage of the solar cell. So we see we plot open circuit voltage, and we kind of get this kind of inverse exponential behavior of the photovoltaic cell circuit model. So let's apply that in an example. We've got a 100 centimeter squared photovoltaic cell, and it's got a measured reverse saturation current of 10 to the minus 12th amps per centimeter squared. So that's actually a current density, right? Because it's per unit area. In full sun, the cell produces a short circuit current of 40 milliamps per centimeter squared. So again, a current density function that we got, or current density measurement that we got here. And this is measured at 25 degrees Celsius. What we want to do is find the open circuit voltage at full sun and at 50% sun. We want to then plot the results. So to do that, we take I0, we were given a current density, so I0 is equal to 1 times 10 to the minus 12 amps per centimeter squared. The PN junction area was 100 centimeters squared, so we take our current density, we multiply it by the cross-sectional area of the PN junction, and that's 1 times 10 to the minus 10 amps. So our reverse saturation current, 1 e to the minus 10 amps. The short circuit current, ISC, we were told was 40 times 10 to the minus 3 amps per centimeter squared, the current density, 40 e to the minus 3 amps per centimeter squared. Again, we need to multiply that by junction area to get the total current, and that gives us 4 amps of short circuit current. And then it asked what is the open circuit voltage at full sun and at 50% sun, and then to plot those results. So VOC, we just need to solve the Shockley equation. It is Q over KT times the natural log of the short circuit current divided by the reverse saturation current, I0. We then add 1 to that. Right? So that's 1.602 times 10 to the minus 19th. That's 3.81 times 10 to the minus 23rd. That's temperature in Kelvin, so in this case 25 degrees Celsius plus 273. We then take the natural log of 4 divided by 1 times 10 to the minus 10. We add 1 to it. That's going to give us 0.627 volts. Right. So since ISC and solar insolation are directly proportional, at halved sun, ISC is going to be halved and ISC is going to be 4 amps. So we just repeat the process. VOC under half sun is going to be this exact same equation, except ISC is going to be 2 amps instead of 4 amps. And so that gives us, we'll make that 100%, and VOC 50%. We use those exact same numbers, but again, we just put a 2 in for the short circuit current since the short circuit current is halved, and we get 0.610 volts. So a small voltage drop due to 50% reduction in solar insolation in watts per meter squared. So the last part asked us to plot these two. So what I did is I just made an Excel spreadsheet. I plotted the Shockley, or I plotted the diode equation. Well, I've erased it now, but it was I equals the short circuit current minus I0 e to the QVD KT minus 1. And so I plotted those for the data sets, and what you get here is this. You get 4 amps at 0 volts and 2 amps at 0 volts for the 50%, and they both have this inverse exponential shape for the current as a function of voltage here. So we can improve the solar cell model that we've presented by adding 2 resistors. We can add a parallel leakage resistance and a series resistance. These are often added to the circuit model to incorporate some of the non-ideal effects of the solar cell. In this model, the ideal current source is still from that PN, is still delivering current to the PN diode, and it also then has another path through our P, and the output voltage is no longer equal to the diode voltage like it was in the previous case because we have this voltage drop across RS. So this is actually a fairly difficult equation to solve. I'm just going to give you the solution. The general solution for this is equal to current flow to the load is equal to short circuit current. Again, this should be ISC here. I'm not sure what happened there. I thought I changed those. Short circuit current minus reverse saturation current, I0. We need to now multiply by E. I'm going to throw in something new here, 38.9. That's KT over Q at room temperature. So you can just go straight to that, 38.9. Sorry, it's KT over Q at room temperature, times V plus IRS. So that's 38.9 times V plus IRS minus 1. And then we need to subtract off from this whole thing minus 1 over the parallel resistance times V plus I times RS. So we've got the equation for current flowing to the load in terms of the short circuit current, the reverse saturation current, the output voltage, the series resistance, and the parallel resistance of the diode. Since the load current I here appears in both the left-hand side and the right-hand side of the equation, there's no explicit solution for either voltage or current, and you have to use numerical iteration techniques to solve this circuit model. The approach is based on incrementing values of the diode voltage V here in a numerical model. For each value of V, a corresponding value of I, and then V are found. So how we do that is we look at the circuit model and we see that ISC, the short circuit current, is clearly equal to ID plus the current flowing through here, ID plus I sub RP plus I. We can solve this and we get, for I, we get I equals ISC minus ID minus IRP, right? So we get I equals ISC minus ID minus IRP, right? This is equal to the short circuit current. ID is the Shockley equation, I0 times e to the 38.9 VD minus 1. And then IRP is just VD over RP. So this equation we can solve using that iterative method, which we're going to apply, whoops, I guess maybe in a later example. I thought it was the next slide. So anyway, individual solar cells typically provide about 5 volts. It's whichever the bias potential across the band gap is. Depends on the material, but typical is about 0.5 volts, 0.5 volts. PV cells, therefore, are arranged in series to produce a higher output voltage, and this connection is known as a solar module. A typical module is going to have 36 cells, and it's going to be rated at 12 volts, even though it's capable of delivering a higher voltage. They're usually downrated. Multiple modules are wired together in series or parallel or both to create what's called a solar array. Like cells, modules wired in series are going to increase total output voltage. However, when more current's required, cells are wired in parallel. So arrays will have different series parallel configurations to develop different power to the load. When the photovoltaics are wired in series, they all carry the same current, and at any given current, their voltages add. The overall module voltage can therefore be calculated as V module is just equal to N times whatever the voltage drop across that diode is minus IRS. So the output voltage is just N, and that VD minus IRS just gives you the voltage at the output terminal, because there's that small drop across the series resistance. So now let's apply that. Okay, so let's apply the idea of the modules and the solar insulation and the Shockley equation. Let's combine it all together into an example using PV cells connected in modules. So we've got a PV module, and it's composed of 36 identical solar cells. These cells have been wired in series. If exposed to a solar insolation of 1 kilowatt per meter squared, each cell is going to produce a short circuit current of 3.4 amps. At 25 degrees Celsius, the reverse saturation current of the PN junction is 6 times 10 to the minus 10th amps. The series resistance of a single cell is 0.005 ohms, and the parallel resistance is 6.6 ohms. What we want to do is find the voltage, current, and power delivered when the junction voltage of each cell is 0.5 volts, and then we want to set up a spreadsheet for I and V and present a few lines of the output for doing the iterative calculation. So what we'll do first is we'll just use our equation. I is equal to ISC minus ID minus the voltage, or minus the current across the series resistance, IRS. We'll just plug our different terms in there. So we were given ISC in the problem statement. That was 3.4 amps. ID is given by the Shockley equation. It's I0 e to the 38.9, I0 times 38.9 VD minus 1, right? So we just need to plug in our VD formula right there. In this situation, or in this calculation, it was half a volt, so ID is equal to I0, that was given as 6 times 10 to the minus 10 amps, 6e to the minus 10, multiply that e to 10, e to the 38.9, multiply that by 0.5 volts minus 1, so ID is therefore equal, actually, I didn't solve that one. I don't know what ID is equal to. I didn't solve that on my notes there. Finally, we've got IRS is just equal to, it's the diode voltage VD divided by RS. So that's 0.5 divided by 6.6. So we get I is equal to 3.4 minus 6 times 10 to the minus 10th e to the 3.89 times 0.5 minus 1 minus 0.5 over 6.6. And we get I is equal to 3.16 amps. There. So we get I is equal to 3.16 amps. The voltage in a module, V module, is just equal to N times the diode voltage minus IRS. So in this case, there are 36 modules. VD was 0.5 volts. We've got I, which we just calculated as 3.16 amps, and we've got RS, which was 0.005 ohms. That gives us 17.43 volts. And then finally, the power is just I times V. The power that the cell can deliver is I times V. That's 17.43 volts times 3.16 amps. That's 55 watts for a solar cell diode voltage of 0.5 volts. What I've done is I've plugged in some similar calculations into a spreadsheet. I've got 36 cells. I've got a parallel resistance of 6.6 ohms. I've got a series resistance of 0.005 ohms. I've got a reverse saturation current of 6.00 times 10 to the minus 10th amps, and I've got a short circuit current of 3.4 amps. So these were the givens in the problem statement. Then what I did is I just iterate VD. I've got VD values of 0.49 up to 0.55. I then calculated different values of I using this equation, ISC minus ID minus IRS. So that's those results. The voltage of the module is therefore just calculated with this formula here, iterated, and then the power of the module is just calculated here with this iterated. So we can see is that as the voltage across the diode increases, we have this different relationship that we would see. So we can plot a VD versus ISC plot if we wanted to for this, or a V module versus ISC plot for that if we wanted to.